So we have covered regulator. We mean that the input voltage is more compared to the output voltage what is generated by the buck regulator. So whenever I want a regulated power supply, and that too with a input voltage which is very much smaller compared to the input voltage, at that time I'll be selecting a circuit which is buck regulator for my use. Okay, so in the last class we have seen the circuit diagram, its waveform and the derivation, and how to design a buck regulator using the critical value of inductor as well as the critical value of capacitor design that we have studied. So in the same way, we have today the next regulator which is called as boost regulator. By the name boost, it indicates that the output voltage will be more compared to the input voltage. Okay, there will be a boosting in the input voltage, sorry, boosting in the output voltage compared to the input voltage what is being supplied to the device. Okay, so this is a boost regulator. With this we have a circuit and then two modes, and we have the corresponding output waveforms. Fine. So we'll talk with respect to this particular circuit diagram. Both of them are same. Okay. So here what happens is this circuit visible?
Yes, ma'am.
Okay. So in this circuit what we have is, we have a power supply, we have an inductor, then we have a MOSFET which is connected with a which is indicated with a M1. It has three terminals: gate, drain, and then source. Then we have a capacitor and we have a diode, then the load. Okay, what is the difference between this and the buck regulator is the placement of your power electronic device. In the buck regulator, if you remember, the power device was here in place of this particular inductor. Okay, and because of this what happens is, we will be operating the circuit in two modes. One is called mode 1 and the second one is mode 2. The first mode, mode 1 is indication that the device is in the on condition, and mode 2 means the device is in the off condition. As usual, what we have covered for step down chopper, step up chopper, the same kind of assumptions we have done. So initially, whenever we talk about a mode 1, the circuit, the power device in the circuit will be on. When we have the thing that mode is 2, then the power device should be in the off condition. Is it okay till here?
Yes, ma'am.
Okay. So during mode 1, when I give a proper control signal to this particular MOSFET, this conducts. Okay. When this conducts, what happens? It acts as a short circuit. So the current flows from this power supply through the inductor. So whenever the current passes through the inductor current rises, and it will be storing the amount of energy, that is EL. EL is nothing but L is into di by dt, that is a change in the current through the inductor. Okay, then the power supply through and back to negative terminal. Okay, this is in mode 1. So that is what we have here. Okay, it passes through this inductor, then through the device and back to the negative terminal. When we don't have any connection between this supply voltage and the load. Okay, so here what happens is, this, whenever it is connected, at that time this will not be in contact with the power supply. Okay, because the current whatever we have from the power supply, that is being flowed through the device which is in the on condition. So the load is separated from the source during mode 1. Okay, then in the mode 2, the device is in the off condition. When the device is in the off condition, it acts as a short open circuit. In that particular case, the inductor which is stored with the energy, it has to be discharging. When it discharges through the diode, and the IL or the current which is there in the inductor, that will be divided into two. One is called the capacitor current and the second one is I0 or IA. That is your average current across the load. So what we have is during this mode 1, when the power supply is feeding the inductor current rises linearly. So that is what we have seen here. Okay, this is your initial value of current I1. This is your maximum value of current I2. Okay. Okay. So what happens is, this is your applied input voltage VES. So after this, what is happening is, no, one second. Yeah. So the inductor current rises for a time duration called as T1. That is nothing but your on period, in which you have the inductor current rising from a minimum level I1 to maximum level I2. Then during the negative half, what happens, or during the off condition or mode 2, there is no supply voltage that is feeding your device. So because of which the circuit, whatever we have, the current will be passing through the inductor, then it passes through the diode, and then it will be passed through the capacitor and then the load. Okay. So what you can observe here is, whatever current which was flowing through the inductor here will be incremental one. That means this part of the waveform. So you'll be having the increment in the current from capital I1 to capital I2. Whereas at that time, what happens, the capacitor is not getting any current. Okay. So the capacitor current what is flowing in the mode 1 is the initial value of capacitor voltage, whatever is stored in the capacitor, or the charge whatever is stored in the capacitor. So it tries to discharge. So the capacitor voltage, if you look at this particular waveform, the capacitor voltage is going on reducing till T is equal to T1 or T is equal to K into T. Then what happens during the negative half during the off condition of the switch, at that time the load current or the inductor current is feeding the capacitor. So at that time the current passes through the capacitor and the charge will be accumulated near the plates of the capacitor, because of which there is a change in the capacitor voltage. So the capacitor voltage increments. Okay. So the capacitor voltage increments up to a point which is called as time period T, or we can also call it as for a duration called as T2. During this period time T2, we have the value of the T, which is 1 minus K into T. That means 1 minus, for a duration 1 minus K into T, the capacitor voltage increments, and whenever you switch on the device again, at that time the capacitor current decrements. This is what is the behavior of the boost regulators, capacitor, whatever is connected here. This is what is about the capacitor voltage. And what is capacitor current? Initially here you can see that the magnitude of the capacitor current is going down. Okay. So we have it as IA, that is minus IA. This is because the load, the load current whatever we have, it is flowing because of the charge whatever present is the capacitor. So I'll be having the voltage or the current at the capacitor to be at a point called as minus IA, and this is there until the duration T1. And at T1, what happens, the current passes through the capacitor, because of which there is a increment in the capacitor current. You will be getting this. Okay. So this, it reaches a point called as I2 minus IA. I2 minus IA is the current what is obtained at the capacitor during the mode number 2. And at T, that is after the time period T2, you will be getting again the value of capacitor voltage becoming 0, and then you will be having the capacitor current continuing to be in the negative direction for the next time period. So this is what is about the capacitor current. Whereas here, this is I1. I1 is the thing, but the initial value of current what is flowing in the circuitry. So for the first duration, there is no value of current, and for the next duration, you will be having this value, say KT into T, or during the time period T2, you will be having this as your input voltage. Okay. And we have this one. This is I0. I naught is nothing but it's the current what is there through the load. So initially during the mode T1 or mode 1 for a duration T1, you will be having the IA current having this particular amplitude, and here also we have the same. So this is because of the inductor current what is there in the circuitry, and this is because of the capacitor current what was there in the load side during mode 1. Okay. Any doubts in the circuit and waveform?
No, ma'am.
Okay. Okay, fine. So with this circuit and these waveforms, we'll now derive the equations for inductor, critical inductor, critical capacitance, and followed by the value for T1, T2, delta I, and so on. Okay, fine. So we assume that the inductor current is rising linearly from I1 to I2 during the time period T1. When we have this one during time T1, what is there in the circuitry is, I have this supply voltage Vs, concentrate only on mode 1. So we have supply voltage Vs, then L into I2 minus I1, because the current is incrementing from I1 and reaching up to I2. This is the what is the change in the current during mode T1. So I'll write it as Vs, which is equal to L into I2 minus I1 divided by T1. And this side I'll not consider because the same supply voltage is not supplying the load. So what is there in the circuit equation is Vs, which is equal to L into I2 minus I1 whole divided by T1. So I2 minus I1, we know that it is a peak to peak ripple current. We'll write it as delta I divided by T1. And if you remember, the same type of derivation we have done it for buck regulator also, and in the same procedure we will be following here. So Vs, which is equal to L into delta I divided by T1, call this as equation number 1. Now I want the equation in terms of small t1. So rearrange this. T1 is equal to L into delta I whole divided by Vs. So this is equation number 2. Fine. Now, yeah. During mode 2, the inductor current falls linearly from I2 to I1. So during mode 2, what all I have? I have the supply voltage Vs and I have the voltage developed across this. This is Va. So Vs minus Va, which is equal to, here there is decrement in the inductor current. So that is negative. So I'll be writing here Vs minus Va is equal to minus L into I2 minus I1. I2 minus I1 divided by T2. So we can write this equation as Vs minus Va minus of L into delta I. This is nothing but I2 minus I1 whole divided by T2, and we'll call this as equation number 3. Now I'll rearrange this equation so that I'll get the value of T2. Okay, so T2 is equal to delta I into L. This is there in the numerator. I have a minus here, so I'll rearrange this equation so that this minus goes off. So I'm just multiplying both the sides with a minus. So what happens is minus Vs plus Va, which is equal to L into delta I divided by T2. So this becomes minus Vs plus Va. So I'll be writing that as Va minus Vs. In the numerator, we have delta I into L. So call this as equation number 4. This is the second step of your derivation. Is it okay till here?
Yes,
Is
ma'am.
it okay?
Yes, ma'am.
Okay. So then what we have is delta I, which is the peak to peak ripple current, can be written as delta I, which is equal to I2 minus I1. And from equation Vs into T1 divided by L. Here I'm just rearranging this so that I'll get a value for delta I. So from equation number 1 and equation number 3. So delta I is equal to Vs into T1 divided by L, whereas here it will be VA minus Vs, sorry, Vs minus Va into T2 whole divided by L, and I have a negative. So this will become Va minus Vs divided by L into T2. So we have Vs into T1 divided by L. This is equation number 1. This is the rearrangement of equation number 3, which is Va minus Vs into T2 whole divided by L. Okay. So, yeah. After this, we need to know what is VA, correct? We don't know VA because until then we cannot cancel out this VS. So what we'll do? We'll do this. Yes. This VA, as we have done it, I think I have skipped some step here. Okay, it's okay, no problem. I'll write down here. Just observe. This is VA, which is equal to 1 over T integration from 0 to T V naught of dt. This is what is the average output voltage equation. So V naught, I know what is V naught, it is equal to Vs. So I'll keep it as Vs and then it is constant, so I'll be taking it out. So the value becomes Vs divided by T into integration from 0 to T1 1 into dt. Okay. When I have this as Vs divided by T into it is average output voltage. So the average output voltage here we can say that it is there for a duration T2. So I'll write down this equation as with limits equal to T2. So I have this as Vs divided by T integration from 0 to T2 1 into dt. 1 into dt is nothing but T. So I have Vs divided by total time period T multiplied with this is small T2. Okay. So this is equation for VA. So equation for VA is this Vs divided by T whole divided by T2, which is nothing but Vs divided by, this is capital T. We know T2 is equal to 1 minus K into T. Okay. So we know T2 is equal to 1 minus K into T. I'll substitute this here. So it will be T divided by 1 minus K into T. T cancels. What is left out is Vs divided by 1 minus K. So we'll call this as equation number 5. Then what I have, Vs divided by 1 minus K is equal to VA. I want the equation in terms of K. So what I'll do, I'll keep this to the other side. So 1 minus K is equal to Vs divided by VA. And this K value, it is the on period. So 1 minus T1 divided by T2 is equal to Vs divided by VA. I'll send this to the other side. So it will be minus 1. Then I have minus T1 divided by T. Take the LCM. So it is Vs minus VA. Okay. Fine. Yeah. Here it was minus T1 divided by T into Vs minus VA divided by T. So here it will be the T sent to the other side. It will be a T, and that I have written it as 1 over F. So this small T1 is equal to VA minus Vs whole divided by VA into F. So this is what is equation number 7. Okay. So from equation number 1 and 3, we have written down the equation for T2. Sorry, small letter T1. Now the fourth part of the derivation, it is, we'll assume that the circuit is lossless and we will be saying that the input power is equal to output power. So input power is Vs into Is, which are using the supply voltage and supply currents. And we have the output voltage, which is output voltage and output current. Okay. Now I have Va, which is Vs divided by 1 minus K, and multiply that with Ia. Okay. Now using this, the average input current, what we can write is Is. Is is equal to 1 minus Ia divided by 1 minus K. This is using this only. Okay. Then the fifth part of the derivation, calculation of the total time period T. So T is equal to 1 over F, we know, and we know also that T1 is equal to, it is total time period T1 plus T2. So we have written a value for T1 and T2 using equation number 1 and equation number 2. Equation number 2 and equation number 4. So substitute them here. You'll be having this as delta IL divided by Vs plus delta IL divided by Va minus Vs. Now take the LCM, so it is Vs into Va minus Vs. Then cross multiplication, I have delta IL into Va minus Vs plus delta IL into Vs. So what is I have here in the next step is delta IL into Va, delta minus delta IL into Vs plus delta IL into Vs, whole divided by Vs divided by Va minus Vs. So what you can see is I have a plus delta IL Vs minus delta IL Vs. I'll be cancelling them out. So what is left out is T, which is delta IL into Va whole divided by Vs into Va minus Vs. Okay. So this is the total time period T, and we call this as equation number 9. Okay. Now I want the equation for peak to peak ripple current, that is delta I. So delta I is equal to, you rearrange this, I'll be having Vs into Va minus Vs whole divided by L into Va, and this T also have, that is written as 1 over F. Okay. Now substitute the value Va, which is equal to Vs divided by 1 minus K. So I'm doing it here, Vs divided by 1 minus K minus of Vs whole divided by F into Vs divided by 1 minus K, and cross multiply, take LCM and cross multiply. So I'll be having Vs minus Vs into 1 minus K whole divided by 1 minus K. In the denominator also have Vs divided by 1 minus K. Okay. In numerator I have Vs and denominator Vs, cancel it out. You will be having the value as Vs minus V divided by, yeah. Okay. So what I have is, I'll cancel out this 1 minus K, and what is left out is Vs minus Vs plus K. So this will be equal to K into Vs divided by F into L. This is equation number 11. Then we'll be writing the equation for delta Vc. So for delta Vc, what we have is, when the transistor is on, the capacitor supplies the load current for the time duration T is equal to T1. That means the capacitor current, whatever we had in the capacitor, that was acting as a load current, correct? And the average capacitor current during your time period T1 is nothing but Ic is equal to Ia. And peak to peak ripple voltage of the capacitor, that is delta Vc, we have to calculate. So this delta Vc is nothing but Vc minus Vc at T is equal to 0. T is equal to 0 means this is the initial value of capacitor voltage. So this is equal to 1 over C, integration from 0 to T1. T1, because in this particular time the capacitor current is being fed to the load, and then Ic into dt. Ic is nothing but your Ia. So I'll write down this. Ia is common, so I'll be taking it out. So Ia divided by C, and integration of 1 into dt is T. So that is equal to T1. Okay. So what we have is delta Vc, which is equal to Ia into T1 divided by C. So we have derived the equation for T1, which is equal to Va minus Vs divided by F. Okay. This is from equation number 7. What we have done here. T1 is equal to Va minus Vs divided by Va into F. So that you substitute it here. So I have delta VC, which is equal to IA into VA minus VS divided by VA into F into C. Okay. Now I have this equation from your VA. So it is VA is equal to VS divided by 1 minus K. I'll rearrange this so that I'll be having it as VA minus VAK, which is equal to VS. So VA minus VS, which is equal to VA into K. I'll rearrange so that I'll be having the value of K, which is VA minus VS divided by VA. That means this part of your equation is turning out to be equal to K. So I have IA into K whole divided by F into C. Following till here?
Yes, ma'am.
Okay. So this is the duty cycle VA minus VS divided by VA. So next what we have, this is your 8th part of the calculation. After I calculate the value for delta VC and delta I, you will be doing what is called as the condition for continuous inductor current and the capacitor voltage. Okay. So for this calculation, what we'll say, if it is the if we have IL, which is the average inductor current, then the ripple current is delta I, which is equal to 2 times IL. Now what I'm trying to do is I'm writing the equation for delta I here, which is equal to 2IL, or it is also equal to 2IA. IA equation I'm writing back. Okay. So K Vs divided by F into L, which is equal to 2 VA divided by R. VA, I know it is Vs divided by 1 minus K. So substitute it here. K into Vs divided by F into L, which is equal to 2 Vs divided by 1 minus K into R. Yeah, Vs cancels. So what is left out here is K divided by F into L, that is equal to 2 divided by 1 minus K into R. Now I want L value, so I'll send L to the other side and rest parameters to the left side. So I have the value as K into 1 minus K into R, that is what is written here, whole divided by K into 1 minus K into R. So I have 2F. So this is nothing but this is the critical value of inductance to be calculated, and this is equal to LC, which is L into K, L which is K into 1 minus K into R. This is what is required for us during the design time, so that I'll be getting a continuous current in the conduction. Okay, and we'll call this as equation number 13. Next parameter what is to be calculated is the capacitor or the critical value of capacitance to be calculated. So if VC is the average capacitor voltage, then the capacitor ripple voltage is nothing but delta VC, which is equal to 2 VA. So capacitor delta VC is equal to 2 VA. In this equation, we'll write down the value for delta VC, and we know what is VA. Okay. The delta VC equation, what is calculated is nothing but we have the value as IA into K whole divided by C into F. Okay. Here, delta VC, what is calculated is IA divided by K into F into C. That is equal to 2 VA. So 2 VA, we can write it as Vs divided by 1 minus K, but I have the equation in the other form, that is in the IA form. So I will write this VA as IA into R. So when I write this one, I have IA and IA common, so cancel them out. You will be calculating it for the capacitor current C. So send it to the other side. So I have K divided by F left out here, and here I have 2 multiplied with R. So C is equal to K divided by 2F into R. This is the value of critical capacitance what is to be calculated, so that I will be getting a continuous average capacitor voltage or continuous capacitor current across the device. Okay. So this is what is the derivation. of the boost regulator. Any doubts?
No, ma'am.
Understood?
Yes, ma'am.
Yeah. We'll do a quick revise. So we have started with this, where the boost regulator is nothing but we have the input output voltage which is greater than the applied input voltage. So the name called as boost. Okay. In this circuit, we have used a MOSFET and we use an inductor and a diode, then followed by a capacitor and a load. Okay. So as usual, we have two circuits, equivalent circuits. One is mode 1 and the other one is mode 2. And the mode 1 begins when the M1 or the switch is switched on at t is equal to 0. So the transistor Q1. By this time you have separated your source and the load because here it is not connected. Okay, when this is not connected, at that time you will be bypassing the load from the source. Then also the load will get a current because of the charge what is stored in the capacitor, and you will be getting a continuous flow of current to the load. Then during mode 2, what happens is the mode 2 happens at t is equal to T1, or at the end of T1, that is equal to K into T. And the current that was flowing through the transistor now will be flowing through the inductor, capacitor, that is L, C, load and the diode. So the inductor current will fall until the transistor M1 is in the inductor current will be falling until the M1 is in the off condition. Okay. And whenever the device is turned on in the next cycle, you will be getting the increment in the inductor current and the energy will be stored in the inductor. So during mode 2, it is the discharge of the stored energy in the inductor. Then after this, we have seen what is happening in the output waveform. So we have the inductor current rising from the t is equal to 0 to kt. So with the upper limit and lower limit, upper limit being capital I2, lower limit being capital I1. And during time t is equal to 0, k into t, at time what happens is the device is in the off condition. When the device is in the off condition, at that time the load is connected to the supply voltage, but it is not supplying the circuit. So the inductor energy, whatever is stored in the inductor, that will be supplying the load. So the current flows from here and it is flowing through the capacitor as well as the load. So during mode T1, what happens? The capacitor discharges. So the voltage across the capacitor is decremental, and the capacitor current, whatever we have, that is in the negative. Okay, it is equal to minus Ia. And during mode T2, the inductor current falls or discharges. At that time, the capacitor current increments, and we will be getting this as your delta Vc, which is the change in the ripple capacitor voltage. Then the same cycle continues for the next cycle when I have the M1 in the on condition. Then we need to talk about these two. During mode T2, the capacitor current increments. So I'll be getting a incremental waveform here. And this is I1. I1 is the current what is flowing through the discharge current of the inductor. So this is I1. So initially it is high and later it becomes less. And it becomes less and it will be having two levels. One is called capital I1 and the capital I2. So the capital I1 and capital I2 are the two limits for the circuit, and with the inductor current being flown. So after this, what happens is we have seen what is called as I average or the average current. So this is constant here because of the capacitor current, here because of the inductor current. So what happens is the inductor current and the capacitor current are flowing through the load, so the load is getting a average output voltage which is continuous. Okay, seen what is called as the derivation. We started it with the KVL to the mode 1 and then KVL to the mode 2. We named it as 1 and 2, 3 and 4. Then it was a time for delta I calculation. We did that, and equation for VA. Then using equation for VA, we have written the value for small t1. Then the assumption that the circuit is lossless, that means there is no power loss in the circuit. I'll be having this Vs into Is, which is equal to Va into Ia. That means the input power is equal to output power. So we'll get an equation for this, and I'll write down the average input current, that is Is, from this equation. Then the total time period T, that is T1 plus T2. Simplification, you will get the value of capital T, or the total time period, is equal to delta I L into VA divided by Vs into VA minus Vs. And we'll call this as equation number 9. Next, what I want the same equation in terms of delta I, so that I can write the peak to peak ripple current across the inductor. So delta I, I'll solve out, and I'll be getting an equation as delta I is equal to K Vs divided by F into L. Then after this, we wrote the equation for delta Vc, which is the capacitor voltage. So for that capacitor voltage, we will be considering the charge that is stored in the inductor because of the capacitor current. And we get a simplified equation, that is Ia into T1 divided by C. Okay. Now what we'll do, we'll substitute the value of T1 from the previous equation, and we'll write this. Then we sort out this particular thing, that is VA is equal to Vs divided by 1 minus K. From that, I'll get an equation for K, and that I will substitute it here. So after this delta Vc, which is the peak to peak ripple capacitor voltage, it is the time for the continuous conduction or the continuous current and the continuous voltage. So to do that, I'll match up the value of delta I, which is equal to 2 into IL. IL is nothing but the load current, so that is equated. And from this, we wrote the equation for LC, that is a critical value of inductor. Then what we have your LC, which is equal to L, that is K into 1 minus K into R divided by 2F. This we will write. This is the equation for your critical value of the capacitance to be needed, so that the conduction happens smoothly and you will be getting a continuous inductor current flowing in the circuitry. And then we wrote this particular thing, which is a delta Vc. So this delta Vc is nothing but Ia into K divided by, that is delta Vc, I'll equate it to 2Va. So after equating, we'll simplify, that is cancellation of the common terms. So you have Cc, which is the critical value of capacitance, to be equal to K divided by 2F into R. So what's the conclusion is, the boost regulator can step up the output voltage within the without the transformer. That means without the application of the transformer in the circuitry, I'll be getting a change in the output voltage. And the circuit uses only single so it has higher. So whatever we have seen, it will be having a higher efficiency, and because of which you will be generating a better circuitry. So all these derivations, whatever you have considered, these are necessary when you try to design a circuit or a boost regulator using the device whatever you have. Okay. So to summarize from the today's lecture, we have learnt about the boost regulator, which is having an output voltage that is boosted version of the input voltage, and we have seen the derivations as well as the waveforms. And here you are trying to understand the boost regulator. So it is Bloom's taxonomy level is L2. So in this L2, you are going to understand, you are going to describe the boost regulator, you are going to discuss about the regulator, its waveforms and the derivations. Okay. So the application where it will be used is whenever a designer is designing a circuit with a more efficiency and he need an output voltage which is more one, or the boosted version of the input voltage, at that time we will be going in for this boost regulator. And the assignment question is explain the working of a boost regulator with a neat diagram and a necessary derivations. Whenever this question is there in the question paper, it will be a minimum of 12 marks, so that you can write the circuit, its equivalent circuits, its waveforms, plus all those derivations. Okay. So if you follow the first one, that is the buck regulator, the second two, that is boost regulator, and tomorrow the next class what we are going to do, the buck boost regulator, the two will be very similar to the buck regulator. Okay. And for your additional reference, you can refer back to the chapter number 5, that is DC to DC converter of Muhammad Rashid text. Anything else to be asked? Any doubts?